This is the video on solutions in colloids. This is part one. For this video, we are going to be primarily dealing with the properties of liquids. We're going to talk a little bit about how solutes will dissolve, how a solution forms, and really how to make sure that we can influence that solubility correctly. In the second video, we'll deal a little bit with solution concentration and those units, primarily a review from 111, and we'll deal a little bit with colligative properties in the next video as well. Alright, so we're going to start off with just a real introduction to what we've been talking about. We're going to start off with what a solution is, which hopefully will be a review from 111, and then we will get into what electrolytes and solubility really means, and from there we'll get into influencing solubility. So remember from 111, anytime you have a solution, you have a solute that's dissolved. That's the species that's there in the smaller amount. So if you talk about salt water, its salt is your solute. You talk about Kool-Aid, the sugar and flavoring is the solute. It's there in the smaller amount. Then you also have the solvent. That is what is doing the dissolving here. Now, in general, guys, we talk about a solution. It's a homogeneous mixture. And so if you think back to 111, that means it's the same all the way through, and you can't really distinguish between the individual components here. Now, also don't get really held up on liquid solution. A solution can be a solid, it can be a liquid, it can be a gas, and you can have solute and solvent with any of those phases. Now, if we talk about probably the most important solvent, it technically is a liquid, and specifically it's water here. Water is the most important solvent because it is so polar. When you think about the water molecule, you have the electronegative oxygen, the less electronegative, partial positive charges on the hydrogens, and that is going to form a really polar molecule that can interact very well with both ionic and polar substances. Now, whenever you have water and a polar or ionic solute interacting, that is called hydrophilic interactions. Here we've got hydro meaning water, and philic meaning, this actually comes from the Greek word for brother or love. So it's water loving interactions. And what's going to happen is you're going to have the water molecule, can I do this? Kinda, not really. Beautiful, right? The stylus is not functioning today. So you have this electronegative oxygen, electropositive sides near the hydrogen, and if you have an ionic compound, say like NaCl, sodium will dissolve into the water, and so it will interact a little bit with all of the electronegative oxygens. This will be surrounded by the oxygen side, and if we had like chlorine, that would be surrounded by a bunch of hydrogens. And it's very, very stable because it goes from having ionic interactions with one or two neighbors to having, oh hey, actually that stylus works better, to having one with many, many, many water molecules, and so it ends up being more stable that way. Now, this does not happen with anything that's nonpolar. Thinking back to the organic chapter, something like alkanes, alkenes, alkynes, those do not have any type of polarity whatsoever, and therefore you're not going to have those interactions that allow for the solute to dissolve. It's going to be more of a oil and water. Think salad dressing, oil, olive oil and vinegar. It's going to be separate. You're not going to be able to have that dissolving. There we go. Now, whenever we talk about those interactions, it's kind of nice to really think about it in terms of um, what is a solute going to do? And the solute is going to take, especially an ionic solute, if it's just a covalent solute, it goes from being in the solid form to the liquid form, or from the gas form to the liquid form, to the aqueous form. Here we've got an ionic compound that's going to split into its cation component and its anion component. So you're going to get 2 potassium ions and 1 dichromate ion here. Now, in 111, we didn't spend too much time here with dichromate. Don't get too held up with this. This is just an ion that could be used. It could be oxalate, it could be chromate, bromate, nitrate, who knows. This just happens to be a colorful solution that we can use. Now, again, it doesn't matter what state of matter you can have a solution that is one of any. So you can have a solution of air. This has got a gas solute, oxygen, like you're breathing right now, and a gaseous solvent like nitrogen. Nitrogen is a solvent here because it's present in 80% of the time. Oxygen is present, I don't know, 22% of the time. So it is the smaller amount, so it is the thing that is being dissolved. Soft drinks have gaseous CO2 that gives it that nice tang, and overall it's in water. I mean, it's got a ton of sugar and other stuff in it, but water is the solvent here. So you've got gas and liquid. You can also have something like gas and a solid. This is the example, hydrogen and palladium. It might be easier to think in terms of like limestone, or really any kind of volcanic rock. When that lava is solidifying and the gas gets stuck in it, the volcanic rock will then have holes where you've got the solid rock, but you also have the solute that is the gas, and it ends up making a really nice pumice type stone. So you can have gas and gas, gas and liquid, gas and solid. You can also have a liquid-liquid solution. Here, rubbing alcohol, you've got isopropanol and water that are being used. You could have salt solid and liquid, where you have a small amount of sodium chloride and a large amount of water. Again, because the solid is there in the smaller amount, it's a solute here. And then you could have solid-solid solution, where you have the combination of zinc and copper. Again, that's that alloy, because you have more copper there than zinc. It ends up being that copper would be considered the solvent. Now, in general, guys, we don't talk about entropy until much later in the semester, but it's just a term for disorder. Now, solutions are going to form spontaneously due to a decrease in internal energy, meaning it's more stable to be disordered. It could also be considered to be the increase of disorder in the system. Again, it's just more stable to be disordered. Now, think about this in terms of your room, your office desk, folded clothes in the closet. It doesn't matter. The refrigerator. You start off nice and neat. You have a closed container with one valve over here, one container over here. If you open this valve, as soon as this valve opens, because these gas particles are moving around, they end up mixing up. There is an inherent progression from neat to messy, from order to disorder within the universe. Whether you consider it here with the gas molecules, or at home in terms of how many times a month do you have to clean out your refrigerator. It is just the way of the world. Now, when we talk about making solution, for the most part, you have to consider how much energy do you have to put in and how much energy do you get out. There's a little bit of an investment that has to go on to make a solution. Now, in the last unit, we talked about intermolecular forces. Well, if you have a solute that is polar or ionic, or even if it's not, you have intermolecular forces holding these particles together. It's going to take energy to break these particles apart and move them away from one another. Whether it's London dispersion, dipole-dipole, or even hydrogen bonding, it's going to take energy. Same thing can be said for the solvent, especially if you have really polar water. Water's got all three of those intermolecular forces. It's going to take a lot of energy to split these apart. Now, what's great though is after you put in energy to break apart the solute, you put in energy to break apart the solvent molecules, you mix them together and now they've stabilized each other. That stabilization allows for overall a net gain in energy. So you put in a little here, you put in a little here, but look at all you get back. Oops. This may be a little bit easier to visualize in terms of a table where you have to put in some amount of energy. You have to break apart the solute, you have to break apart the solvent, but then the overall stabilization of the polar molecules and the polar solvent or nonpolar solvent gives you overall a lot of energy back. And so even though you had to put some in, you have a net gain of energy here. Now, if you have a solution where you've got maybe a nonpolar solute and a polar solvent, here you're not going to get as many intermolecular forces of that solution and it's not going to stabilize. So you're still going to have to put energy in to break apart those solute and those solvent molecules from one another. But when you put them together, because they're not interacting very well, you don't get as much energy back. And so overall you have a net increase in energy. This is something where you have to continually put energy in to have a solution. Again, think oil and vinegar. You have to continually stir that to keep it in solution. Now, if we talked about hydrophilic interactions, hydrophobic interactions are basically the opposite of that. Hydro meaning water, phobic meaning it doesn't like, so it doesn't like water here. So in general, when you talk about having a hydrophobic or a nonpolar oil, remember these are, why is this not working? There it goes. If you have a really long alkane, this doesn't have any way to interact with water. And so what it's going to happen is in water, if you add oil, it ends up being that the oil molecules will line up and kind of associate with one another. And then water will associate with itself. And that's why you kind of see the droplets of oil on the top of water in the pan. It's just a, it's more stable to be nonpolar with nonpolar, polar with polar. The key here, guys, is like dissolves like. Polar solutes go in polar solvent. Nonpolar goes to nonpolar. Now, at this point, please just pause and think about why it is that you have solutions like oil and water not mixing. So just hit pause, think about it, and then all I want to say is really, guys, oil is a mixture of nonpolar molecules. That means that they only interact through London dispersion forces. And the only thing that can be affected by is molecular size. So technically your delta H is going to be overall very small for those molecules. The only thing that can make it even slightly large is going to be large oil molecules. Then on top of that, so you have a large H1, large H2, but then when you try to put the H3 together, the nonpolar and polar molecules don't interact, so you get very little stabilization energy back. So you put in a lot of energy to break apart the solute and the solvent, get very little stabilizing back, and so that can't make up. So you end up having overall a positive delta H, and so you're going to have a net positive change here. Okay? Now, if you have a hydrophilic interaction, whether you've got the dipole-dipole, hydrogen bonding, it doesn't matter, one of those is almost guaranteed to allow the solution to form. And that's because you have nice ionic compounds, water, they're both polar, and so they can interact. Now here's what I consider my flashcard slide. You've got the different types of solutions that can be formed. Polar solute, polar solvent. Yeah, it takes a lot of energy to break apart the solute. It takes a lot of energy to break apart the solvent. They're polar. That means you have at least dipole-dipole and London dispersion forces here. Dipole-dipole forces are big, so it takes energy to break apart those forces. But you put them together, they're both polar, so they're going to stabilize each other. So you're going to get a really big piece of energy back. Negative means it's leaving, it's coming out, you're gaining that. And so your overall delta H of solution is going to be negative. You're going to be stable to form that solution. It's going to be a small negative because of large energy input eating up some of your profits here. But in general, it's going to form a solution. Anytime you have a nonpolar and polar, whether it's nonpolar solute or polar solute with the opposite solvent, it's going to take a little bit of energy to break apart the nonpolar substance, where you have just London dispersion forces. A lot of energy to break apart the polar substance, where you've got dipole-dipole. But because they do not interact, there is absolutely no stabilization here. You get very little energy back, and so you end up having to put a lot of energy into keeping it in solution. If you've ever had oil and vinegar salad dressing, you mix it, you use it, within 30 seconds it's split back up. You have to mix it for the next person as well. No solution forms. It just doesn't work. Nonpolar solute, nonpolar solvent. Okay, this is all going to be London dispersion forces here. A little bit of energy to break apart the solute, a little bit of energy to break apart the solvent. You get a little bit of stabilization when you mix it up. So you get a small net increase in energy, or energy that comes out. You gain that energy. So you get a solution. But again, like dissolves like. Nonpolar, nonpolar, solution forms. Polar, polar, solution forms. So guys, in general, like dissolves like. If the more energy something takes, the less likely it is going to be to happen. And it really has to do with what type of solute, what type of solvent you have. Really, liquids and gases, mixing with liquids and gases are the easiest, just because of the movement involved. The rest is up for debate. Now, talking about solids going into liquid form. When you have a solid ionic compound and it dissolves in water, it's going to split into its ionic components, which is going to allow it to be an electrolyte, which is just something that conducts electricity. Now, you can have a strong electrolyte, a weak electrolyte, or a non-electrolyte. And I don't know how long it's been since 111, so just as a review, we've got strong electrolytes that completely dissociate in water every single time. Doesn't matter if you add 100 molecules of this, every single one is going to split into its ionic components. Ionic compounds that are strong electrolytes are going to be usually from group 1 metals, the ammonium compounds, the nitrate compounds, things like that. Weak electrolytes will conduct electricity, but it's going to be not as well. So if you added like 100 of these molecules to water, maybe 95 would dissociate, but that would be about it. So these are ionic compounds that are partially soluble. Things like acetic acid or weak acids, weak bases. Those are weak electrolytes here. Non-electrolytes do not dissociate in water at all, and because they don't have ions, they don't conduct electricity. These are generally going to be like covalent compounds. Usually they have to be polar though, so something like ethanol or glucose. It has to be either soluble and not dissociating, or insoluble, something like silver chloride. Now again, I don't know how long it's been since you've had 111. So I wanted to just briefly review the solubility rules. In terms of solubility rules, nitrate compounds are always soluble. There's nothing you can pair with a nitrate to make it insoluble. Group 1 metals, ammonium, and acetates are always soluble. So these are a good bet to be strong electrolytes. The only difference, the only exception is acetic acid, so acetate with an H. Chlorides, bromides, and iodides are almost always soluble, so they are strong electrolytes, unless they are paired with silver, mercury, or lead. Silver bromide, mercury chloride, lead chloride. These are insoluble, so these compounds with these guys are a non-electrolyte. Sulfates are soluble unless they're with barium, calcium, mercury, or lead. If it pairs with one of those, that becomes insoluble and therefore a non-electrolyte. Hydroxides are not soluble unless they're with barium, calcium, group 1 metals, or ammonium. At that point, they become very, very soluble, and so these would be strong electrolytes. Anything else with hydroxide would be a non-electrolyte. Same thing down here. These generally are going to be non-electrolytes unless it's paired with a group 1 metal or ammonium. So just as kind of a visual, something like ethanol or glucose, or even a non-soluble compound, is going to be a non-electrolyte because there's not going to be any ions in solution here. Something like acetic acid is going to be a weak electrolyte because only some of them will dissociate, so you have ions but just only a couple. Whereas strong electrolytes completely dissociate all the time, and so there's a lot of ions in solution, and there's going to be high conductivity. Now, in general, we want to quantify the solubility of a compound. Now, solubility really just means the maximum amount that can be dissolved, okay? Now, at that situation, you have solid on the bottom of the beaker usually, and so you have stuff down here, and the solid is dissolving. The stuff that's in solution goes back to the solid form. You have as much in solution as you possibly can. Now, that's when you have just the right amount of solute that can be dissolved. It's saturated. If you have less than the maximum amount, it is unsaturated. And if you have more than the maximum amount, it is supersaturated. Now, the only way to really make a supersaturated solution is to basically heat it up or something like that, dissolve some sugar or salt, and then bring it back down to a temperature where it shouldn't be soluble. And you have to really try to make a supersaturated solution. Now, there are things that affect solubility. Primarily structure, what kind of intermolecular forces are being used here, and then there's temperature, agitation, and pressure, and we need to talk about all of those. Now, guys, in terms of how these affect your solute, it really depends on whether you have a gas or a solid solute. So for example, for a gas, you talk about gas in a soda, for example. If you leave your soda out, it warms up, it gets to be flat because gases are not very soluble in high temperature. So you want low temperature to maximize that solubility. Same thing, if you've ever dropped a soda and then tried to open it, you know that you've basically knocked that gas out of solution. And so you want to have low agitation to maximize the solubility of a gas. And then finally, high pressure. They don't just make a soda and then leave the top with the same pressure as the room. They add a whole lot of gas pressure there to really ensure that there's an equilibrium in keeping it saturated with carbon dioxide for your soda. And you know that there's a lot of pressure because when you open it, you hear that shh of all the gas escaping. So just as an idea, the more you heat up a solution, the less gas is able to be dissolved. Now you can also think about this in terms of other situations. You leave a glass of water out, you can actually see the gas bubbles dissolved. So there really is gas dissolved everywhere. You have to use a gas box or an anaerobic chamber in lab. You actually will pull a vacuum on the liquid and remove the oxygen and nitrogen dissolved and fill it back with argon, and do that a few times to really try and minimize the amount of oxygen that's in the solution. If you are near and I forget where this is, if you're near a factory that's got temperature pollution, if your temperature of the water gets too high, there's less oxygen dissolved, and you can actually have wildlife that's negatively impacted there. It's also why you're not supposed to have a fish tank near a window, or you're not supposed to just let it go. You're supposed to monitor the temperature there. Same thing, if you heat it up or you stir it, the gas becomes less soluble and it will leave. On the other hand, we could talk about liquids. You want liquids, if you're going to maximize the solubility of a liquid solute, you need to have structural effects that are going to allow for the same type of intermolecular forces. You can have two hydrophobic or two hydrophilic liquids forming a solution, but they have to be of the same type, okay? Hydrophobic, hydrophilic liquids will not be miscible, and so they will not form a solution. So again, oil and water doesn't form a solution. You want it to be the same. In terms of solubility of solids, solids are interestingly different from gas solutes. Here you want high temperature. If you ever think about adding sugar to tea, if you have iced tea at a restaurant and you add sugar packets, it goes straight to the bottom. So you end up getting like crunchy sips of tea from the straw. It's not very soluble. On the other hand, if you make it hot and add sugar while it is hot, like local restaurants do, you get tea that is almost syrupy in composition. So you can maximize the solubility of solids by heating temperature usually, and by stirring or getting at high agitation. And then finally, you just really want to make sure that you have a solute that is going to have the right type of interactions. So again, in general, I'm not going to ask you about exceptions. As you heat it up, things like sugar and ionic compounds become more soluble in water. Excuse me. You can also think about it in terms of how that solubility can be affected for things like hot packs or ice packs. Here you've got a supersaturated solution. You click the little coin, which is a catalyst for crystallization. That crystallization releases energy that translates into making it a nice hot pack. So that's where this is going to end. We have at this point covered, how do I go? We have covered the properties of liquids. No, we've covered the properties that affect how a solution is formed, and we've covered a little bit on the intermolecular forces present. In the next video, we'll get into solubility units and colligative properties.